Hey folks, hope you're ready for an extra large bundle of news. First up, on Tuesday, July 14th, Unreal Engine will host their first ever Unreal Fest Online, a free one-day virtual event combining Unreal Fest and Unreal Academy to offer an exciting and informative program of sessions that are open to everyone. Choose between 5 content tracks from across architecture, automotive, games, film, TV, and live events, and cross-industry with over 50 sessions in total, plus more on Unreal Engine 5. Visit unrealengine.com/UnrealFestOnline for the full agenda and to register today. While you wait for Unreal Fest, get a sampling of new presentations from the Unreal Engine Evangelism team on building advanced effects in Niagara, creating photoreal environments with megascans, and producing natural environments with terrain and landscape tools in Unreal Engine. All 3 are available now at youtube.com/UnrealEngine. Did you miss the original featured free marketplace content? No worries. All 5 items in the first free content round have been unvaulted, in addition to 5 more free packs from each of the original contributors. Download magic effects, dragons and farm animals, picturesque landscapes, low-poly cities and burbs, a scientific lab, and a scenic fantasy town. If that wasn't enough, Iliad, the in-engine blueprint brush creation system, and a level design assistant plugin are now permanently free. Visit the Unreal Engine Marketplace to collect them all. Speaking of free items, a new Control Rig Mannequin sample project is also now available on the marketplace. Introduce yourself to Manny's new rig and download the free example to explore Control Rig, which enables you to fully rig and animate characters directly in Unreal. Download it today. Developed by Riot Games, Valorant is a free 5v5 tactical shooter matchup in which you plant or defuse the spike. Valorant relies on Unreal Engine to provide a solid baseline that enables the devs to focus energy on the game's key differentiators. Gain insight into their strategy from their principal software engineer, Reid, on the Unreal Engine feed. Sourcing from our own experience creating games like Fortnite, we put together a brand new guide to help you streamline editor updates and distribute the Unreal Editor to your team. Visit the Unreal Engine blog to read the full white paper, Workflow on Fortnite, Collaboration on large teams with UnrealGameSync. PlayStation's Future of Gaming reveal event provided a look at many of the games coming to PS5, from the long-anticipated Little Devil Inside and a stray cat exploring neon-lit cyber cities, to heavy hitters like Godfall. Take a peek at the Unreal Engine titles that shined at the event. Are you a student creating in Unreal? We are seeking even more outstanding content from students to highlight in our Fall 2020 Student Showcase. Review our recommended guidelines and then submit your project now for a chance to be featured. Have you ever wondered how an astronaut prepares for their time in space? Before lifting off in 2021, the Boeing Starliner crew will simulate their mission for hundreds of hours in Unreal Engine, augmented with the unmatched human eye resolution and fidelity of Varjo's VR headsets. Discover how, together, Varjo and Boeing are ushering in a new era of space flight preparations at varjo.com/Starliner. And now for the wonderful folks sharing their gifts of knowledge on AnswerHub. Clockwork Ocean, Renee Zwan, Everynun, Tsumi Saki, Churer, Mamamarsis, Nuwai, F Innovations, Daniel the S, and Ali Akbar. Thank you all so very much. On over to our community spotlights. This gorgeous cinematic is Battlesuit, an animated short directed by Hazraf Haz Dalol. Adapted from The Theory, Battlesuit tells one of many stories about an astroarchaeologist working to save our future and a time traveler working to save our past. Watch the full film at hazfilm.com/battlesuit. Tom Clancy, professional developer and son of renowned author Tom Clancy, now hosts the That Tom Clancy Show on Twitch, where he discusses current events, entertainment, and other elements of nerddom as a robot. The show is driven by Unreal and features guests from a variety of backgrounds. Watch the That Tom Clancy Show at twitch.tv/thattomclancy. Venture into a world inspired by the Western Isles of Scotland in Sky, a relaxing, explorative game. Fly around the captivating islands, help the locals, and set the fastest time in races while absorbing everything around you through the painterly environment. Check out Sky in early access on Steam. Thanks for watching this week's news and Community Spotlight.
Hi everyone and welcome to Inside Unreal, a weekly show where we learn, explore and celebrate everything Unreal. I'm your host Victor Broden and my guest today is Principal Software Engineer Marcus Reid from Riot Games. Welcome to the show.
Hello, thanks for having me.
Well, today we are here to talk about Valorant.
Yeah, so if you haven't played Valorant yet, it's a 5v5 tactical FPS with character abilities. It's played over a series of up to 25 rounds, first team to 13 win. Attackers are trying to plant a spike on some pre-designated bomb sites, and defenders try and either stop the attackers by killing them or by defusing the spike after it's planted. We have really fast, tight gunplay. Lethality is incredibly high. Time to kill is incredibly low. So when we're trying to create a good experience, those fractions of a second really matter quite a bit. A single headshot with most guns is enough to score a kill. So today we're going to talk a lot about some of the unique performance challenges Valorant has in a bunch of different configurations, and also some of the optimizations we've done to solve those challenges.
Yeah, I was playing a little bit earlier today and it's definitely gets your heart pumping when you're on one of the last rounds or you're one of the last players standing and everyone's sort of telling you in voice chat like, come on, you can do it, you can do it.
Yeah.
It's a good game. I'm ready for you whenever you are.
Sure. So I'm going to talk about a little bit about server performance, then I'll talk about performance of some of our minimum spec machines, and then we'll talk a little bit about high spec performance. And all of those are very different. The things that we have to optimize for vary by that configuration. So let's kind of dive right in and start on server performance. In Valorant, all of our servers run single-threaded, and we run 128 ticks per second, so that's 120 frames per second. That kind of gives us a total frame budget for a single server frame of 7.8 milliseconds. And we actually try and run 3 games per CPU core. So the real amount of work that we get to do per frame is just 2.6 milliseconds, which is not a lot of time. We chose 128 ticks based on a bunch of internal testing, and that's kind of where the game felt best in terms of minimizing peeker's advantage, and again, making sure that you have that really, really quick responsive gunplay. So the first image I'm going to show here is what our server performance looked like in May of 2018. The first thing we did when trying to get server performance to a state where we were happy is we went through the engine and through our game code. We added a bunch of instrumentation and we bucketed time by subsystem. So what you'll see here on the left, all of these different rows are the different subsystems that we measure, and these are just timings over time. So if we look at that May 2018 column, you'll see our total average frame time on the server at that point in time was 11 milliseconds. So actually, back then, we couldn't even run the game consistently at 128 frames on the server. We were just too slow. The big buckets of time that we were spending were the replication system, the network system, the animation system, and then it sort of trails off on the systems further down from that. For most of this example, I'm going to be talking about that animation subsystem, which you can see here is 1.4 milliseconds per frame. If you think about that in terms of our 2.6 millisecond frame budget, that's 54% of our total budget. So that had to come way down. We also had to optimize all these other systems, and there was a ton of work that went into that, but I'm going to focus specifically on that animation example. In Valorant, our server is authoritative. We don't trust clients for movement or for shooting. Everything runs through the server. That's to protect the competitive integrity. And what that means is that the clients are actually running a little bit in the past in terms of where the simulation is. That's because of client latency, your ping time between you and the server, and also just the frame times being different on the client versus the server. So why do we even do animation on the server? Is an animation something that's just cosmetic? For many cases, that's true, but it is important for hit registration. In order to determine whether or not a bullet hits a target, we need to have accurate bone positions for that target. So the server has to compute animation for all the different characters in the game in order to know where their bones are. And then when a gunshot happens, the server has to rewind the game simulation, rewind time back to the point in time that the client observed when the player pulled the trigger. So if you think about, like, say you've got a 50 millisecond ping, which is not actually very good. The server, when it's running frames 7.8 milliseconds, that's going to be about a 6 frame difference. So the server actually needs to rewind the simulation back between 6 and 7 frames, look at where bones were on those frame intervals, and then for subframe time offsets, we can interpolate the bone positions between those spots. Anyways, I'm kind of getting off into the weeds, but to come back, how did we make animation fast? The first thing we did is anything that wasn't involved in hit registration, we just turned off on the server. So anything in the world that's animating that can't be shot, we don't need to simulate it on the server for animation. Also, Valorant is played over a series of rounds. The first stage of every round we call the buy phase. And during the buy phase, we drop big spawn barriers across the map, and the teams can't interact with one another. You can only interact with your own team, and we don't have friendly fire. So while we're in the buy phase, we don't actually need to have the server do any animation work at all. We can turn it off entirely. And that saves us a good amount of time on average, especially when you start loading up servers with a bunch of different games running concurrently. So after that, the next thing we can look at, I've got 2 clients here running on my machine as well as a game server. This is all just local. Let me show you what the hitbox actually looks like from the server's point of view. So this red outline that you can see is the hitbox for Sova, and we actually used the same hitbox for all of our characters. Even though the character silhouettes are a little bit different in terms of shape, we use the same hitbox for competitive integrity. So you can see the server hitbox is tight. It's following Sova. If I move around on this client to the right, you can see it tracks pretty accurately. And right now, the server is running animation every frame for Sova. Let me have my enemy automatically strafe back and forward here, just so that you can kind of get a visualization without me having to manually control it. So one of the first optimizations we looked at after the naive, let's just turn things off, is can we rate limit this animation? Since we're going to be doing interpolation for subframe offsets anyways, what is the biggest window of interpolation that we can tolerate and still get a good hit reg result? You can tune the rate of animation evaluation on the server. And if you go too extreme with this, I'm going to actually say, let's only animate every 128 frames, which is once per second. You're going to see that hitbox is just absolute garbage. It doesn't update well enough to give you a good result. If I bring it back down to 1 frame, you can see it's tight. But if I increase it to, say, 3 frames, even though you can potentially get a tiny bit of error, it's basically not visible. So by rate limiting that update rate, we're increasing the range of snapshots from 7.8 milliseconds to about 23 milliseconds. The amount of error you can accrue is only, what's the difference in that leg or that arm movement in that 23 millisecond window versus that 8 millisecond window. And we can still do that smooth interpolation between those positions to compute positions for offsets within that time window. So we played with this a bit. We did a bunch of tuning. It produced okay results, but it still didn't get us anywhere near the perf goals that we had. Just paying for animation so frequently was too expensive. If you look in the code of the engine, in general, there's an update phase, which is relatively cheap, and there's an evaluation phase, which is very expensive. And the way we do the snapshotting of the bone positions is we ran through the full evaluation, we wrote down the bone positions, and then we did the rewind, we restored them and did that interpolation that I mentioned. But paying for that evaluation is the critical part that just didn't work for us. So the next thing we did is said, okay, let's say we don't snapshot the bone positions. What do we need to compute the bone positions if we wanted to do that on demand? And it turns out if we go through and if we snapshot all the state and all of the individual anim graph nodes, we don't need to do the full evaluation and get the bone positions. Instead, we can just capture that state, restore that state when we need to do an on-demand evaluation, compute the bone positions, and then run the hit registration from that on-demand result rather than having to snapshot the outputs periodically. Let me show you what that looks like. Server and that one. I actually need to transition to a new phase for that setting to take. All right. So now what you're going to see is the server is no longer doing any animation. The hitbox is totally wrong right now, but it is keeping track of the inputs to the animation graph. So just to make it really apparent, let me turn on our client hitbox as well. So the client hitbox is actually accurate in this case. The server hitbox is inaccurate. You can see the feet are out of position. The arms are out of position. The head is a little bit higher than it should be because Sova is actually ducking a little bit in this idle pose. we're basically just in a reference pose. And if I do my same auto strafe here, you're gonna see that hitbox just slides back and forth. So that's not correct. That would produce really bad hit registration results. If I shoot a bullet close to Soba, what you're going to see is that server hitbox snaps to where he was at that point in time. So that's the on-demand evaluation happening. And now we're only paying for animation when we're actually in a gunfight. This is what produced the really good results for us. There's one tiny optimization we can do on top of that, which is if you think about it, we need the accurate bone positions to know whether a bullet hit. But if a bullet is way out in the middle of nowhere, if I'm shooting all the way over here, there's no reason to pay the cost of animating Sova because there's no way that was going to hit. So the way we would determine that before we do the rewinding, we actually shoot a giant sphere cast down the shooter's aim vector, which you can see here. It's long enough to go across the entire map. It also penetrates walls, which is important because we do have surfaces in the game that you can penetrate with bullets. Anything that collides with that sphere cast, that's what actually triggers the animation update. So you can see these green dots are points where I had collision. But if let me spawn some fake characters here. What you'll see here is if I shoot off to the side, no updates, still in that same reference pose. But the moment I start to get close, those hitboxes are going to snap to the right position. We'll do the update. And yeah, that's how we can do hit registration to get kills. So up until the point where we started actually modifying the animation graph, this was all pretty straightforward to do in stock Unreal without a ton of modifications. When we started snapshotting the state on the anim graph, that's where it kind of got expensive because now in our code, we have to understand each individual type of animation graph node. We have to understand all the state that goes into each node. And the thing that maybe isn't obvious, that's the biggest cost, is now whenever we upgrade our version of the Unreal Engine, we need to carefully review any changes to anim graph nodes, make sure that our snapshotting logic knows how to handle any state that was added or removed. And we also need to handle new anim graph nodes when they get added. So by modifying the engine to get this optimization, we're signing up for an ongoing support burden to make sure it keeps working as we continue to upgrade to new versions of Unreal. So to just kind of show where we landed after that work, if I can get control of my cursor here. This is animation data for this is subsystem performance data on the server for the last 10 weeks. You'll recall where we started, animation was at 1.4 milliseconds. Now it's down around 0.26 milliseconds. So that's like a 5x improvement. And this is kind of where we're running today. We're well within budget on that total 2.6 millisecond frame budget for the entire server frame. It does occasionally go up and down. You can see there was a point in time here where we had a regression and everything got more expensive. But we track these metrics over time and make sure that we stay within our budgets. And that gives us a solid 128 ticks on the server. You might also notice I've got this render subsection down here that's constantly at 0. That's because the server doesn't do any rendering. And you might wonder, hey, why is rendering even on this chart? And the reason is because we build this chart for clients where the rendering subsystem is not 0 cost. So I feel like that's a pretty good example of server performance. If there are any questions about that, I can speak to those, or I can move into min-spec performance.
Let's see, specific to server. Are you using movement prediction?
Yes, we do.
I'd say the rest of the questions are general, so we can leave those for the end.
All right, cool. Well, low-spec performance looks quite a bit different. Our minimum spec machine is a laptop from 2012 with an integrated GPU. It's the Intel HD 4000. That graphics card is not very powerful. So on our minimum spec machines, we tend to be entirely GPU bound. That laptop also doesn't have a very nice CPU, but by and large, how fast we can render stuff is the thing that becomes our bottleneck. So we've spent a ton of engineering effort getting to the point where we can run a solid 30 FPS on that machine. In fact, we do a little bit better than that. In a lot of scenes, we can get up to 45 or 50 frames per second, which is pretty good. Something I do want to call out when we're targeting hardware that told, it's got engineering challenges in it, but it's not an engineering problem. And there's no amount of code that engineering can write to solve that problem in a silo. It really relies on artists fully committing to those targets and accepting some pretty egregious constraints on what they're allowed to build. So I want to call out that like our artists are really heroes. They have to come up with lots of creative solutions to make the game look good and still run performantly on that older hardware. So the way we go about doing that is we defined a bunch of budgets early in the product's life cycle around how much VRAM can you use, how much budget do we have for light map textures, what texture resolutions do we accept, how many triangles do we get in a given scene. And the metric that has kind of been most useful as a proxy for real world performance is just like how many draw calls we're issuing. I'm mostly going to talk about the maps and the environment here, but our environment team tries to keep any given scene in the play space under 600 draw calls, which is not very much. And even with all these budgets, they're really good proxies for overall performance, but they're not a substitute for measuring on the actual hardware. It is not uncommon for us to be surprised about how performance scales on the minimum spec machine versus our development hardware. Things that we think are fast have been slow, and things that we expect to be slow often have no noticeable cost. So it's really important to regularly measure on the machines that we're actually targeting. Um, so to that end, every week we now collect performance captures on our main maps, which is what this image is on the screen right now. You can see that on Haven, our most expensive scene that we're measuring right now is A-Site, which is about 30 milliseconds. If you look at Split and Bind, which are two of our other maps, most of the scenes are around 20 milliseconds, which is going to be about 50 frames per second. You'll also notice here that we had an actual increase on the timings from this test to the next one. That was a regression in code. It didn't show up on our high spec development machines. It only showed up on the minimum spec. So that is another good example of like why it's so important to measure on actual hardware. The way we capture this data is we load up those scenes on the minimum spec laptop, and we use Intel's GPA to take a scene capture. We then go through that scene capture and look at the individual render passes as well as the total timings for the scene. And then we capture all that data and we just track it over time. I'm going to quickly show kind of a more detailed breakdown of what that report looks like. Don't worry too much about the details here. I'm going to come back to it after I step through some of the stuff that we have in Editor. But the gist of it is we capture full frame times, we capture delta timings from test to test. So, I mentioned we had that regression where things got a lot worse in the June 10th test. You can see in the June 11th test, we mostly fixed that. And then each column here is one of the individual render passes that we've defined for the game. I'll talk a little bit about what those are before we look at the numbers. So if I pop over to the editor here, the first thing to call out, like it is just the Unreal editor, but you might see some things that look a little bit different from what you're used to. The reason for that is way back in the day, nearly 4 years ago at this point, we did an evaluation of Unreal's deferred renderer at the time, and we just could not hit the perf targets that we needed on the hardware specs that we wanted to hit. So we ended up building our own custom forward renderer based on Unreal's mobile pipeline at the time. So one of the things that you might notice here is this is actually the editor running in mobile mode, which is not something Epic ever really intended. But we basically lie to the engine and say we're one big phone, and we have fixed several bugs related to running the editor on what it thinks is one big phone. Since we did that work, Epic has added the forward renderer on the desktop path. I think that was added in UE 4.14. We aren't using that because our implementation predates that work. If we were starting today, we would probably use that as our foundation rather than the mobile pipeline. Let me fly around and just kind of show draw calls for a variety of different scenes in the map. So this column right here is the one to watch. You'll see right now I'm up at around 400 draw calls. As I come through here, it's going to drop to 200 or 300. In general, most of our scenes in the play space are actually down under 400 draw calls. 600 is our hard limit, but we like to keep it lower whenever possible. And just stressing again, like this is a ton of work from the environment team. When we get over into the spawn areas where the game starts, we don't expect much combat here, so we have a little bit more flex on the budgets. So you'll see here we're actually up to 550 draw calls. These tend to be our most expensive scenes in terms of rendering, but they're also not the hot play spaces. There aren't a bunch of gunfire and abilities in those areas. Yeah, as I fly through here, 350 draw calls when I get onto site, 200, 300. Pretty low draw call counts.
That is low indeed.
And to achieve that, we do tons of instancing. A lot of that is manual. It's a lot of work, but it ends up being worth it to be able to run on that hardware. All right, so other things that we've done, I mentioned that we had the custom forward renderer. We've also defined our own render passes and our own shading models. We have 3 shading models that we use. We have one for the environment. We have one for first person weapons and arms, and we also have one that we use for characters in third person. All of those shading models have their own shaders that have just the minimal set of features that they need. We have basically no extra frills, especially when you turn down our material quality settings to low. The primary shader that we use for walls in the environment, when it's scaled down to low, I think it has like 39 pixel shader instructions. So it is super, super light. Another thing that's like sort of interesting is, since we really want to protect that competitive integrity, we do not want to vary the world state too much between low and high. It's important that you get good clarity and readability on all of those settings. So when we move to low, we'll take out some detail. You'll lose like normals on the walls, and you won't have it'll look a lot more flat, basically. We also will remove some decals and some other things from the environment that don't really affect gameplay, but we're never going to do something like cull out a potted plant that someone could be hiding behind. It's important to us both that players on older hardware get a good experience, but also players on higher end machines don't feel compelled to go down to low quality settings just to try and get some competitive advantage. We've seen that in some games, and it's a behavior that we don't really like. We want you to be able to play on high spec and feel like you're at a disadvantage with high quality settings. Other than the shading models and input to that, we made heavy modifications to the material editor. We have a bunch of pins that aren't in stock Unreal. And we also don't use all of the pins that are in stock Unreal because we can't afford them. We have a depth prepass or a Z prepass where we draw to depth before we run our base passes and evaluate whether or not we should run the pixel shader. Stock Unreal has a depth pass. The way it works in stock Unreal is it takes all of the meshes in your scene, it draws them to depth, and then you move on to the base pass. What we found on our lower end hardware is the overhead of incurring all of those individual draws was too high. So the way we handle that, we have an offline process where we basically build one giant mesh for the entire level. It's simplified. It doesn't have all the detail, but it does cover all of the big shells and walls and floor. We draw that single mesh to the depth buffer instead of doing all of those individual draw calls. And it's not an especially elegant solution, but it is the solution that gave us the best perf results in all of our testing. In 422, with the big mesh rendering pipeline refactor, there's now automatic draw call merging in the engine. We still have work on our end that we need to do to be able to take advantage of that, but I'm optimistic that that approach can produce a better result than our giant prepass mesh. So obviously we need to do the work to get on board with that, and then we need to evaluate it. But if that pans out, that's a good example of a piece of tech that we built that we will probably sunset in favor of Epic's supported solution. The other thing that's sort of important to our rendering, we don't do any distance-based culling, so you can see everything all the way across the map. You won't see a mesh pop in or out based on where you're standing. We do the normal frustum culling, and we also use Umbra for occlusion culling. Given that we have no distance limits, occlusion culling is incredibly important. If I turn that off, you're going to see I'm going to jump from 400 draw calls up to probably close to 3,000. Yeah, so the game would be unplayable if we had 2,900 draw calls firing all the time. It helps a lot. It's not perfect. I can show you. Turn off scene rendering and let me freeze my rendering here. So this will pulled the culling results, you can see what was in and what was out. You can see we do a pretty good job here. We got most of these big shells, but this floor here is still getting drawn, even though it's not really visible. Part of this wall was occluded, but you can still see it. So I fly through here. This wall is the bane of my existence. Can't get occlusion culling to take it out. The reason for that is if you look at it from this angle, that blue spawn barrier that you can see off in the distance, that's where I was standing. And this wall is peeking up just over the top. So since the wall is there, we can't pull it out because you could position yourself just right to get a few pixels of it, and we do actually need to draw it. But that's where the Z prepass becomes really helpful, because even if we have a little bit of overdraw, if we're not paying the cost of the pixel shader, by and large, we're going to early out and not incur too much cost there. So I mentioned that we use GPA for most of our performance captures. We also use RenderDoc a lot internally, just for measuring perf, or not for measuring perf rather, but for doing debugging of graphical issues. If you haven't used it before, in the engine, there's a built-in plugin, that RenderDoc plugin. If you have RenderDoc installed in your machine, all your viewports are going to get this little button, and this little button is wonderful because when you click it, it will take a capture for RenderDoc and it'll just boot up the application with the scene that you captured. As of 423, the engine is also smart enough to detect when it's running underneath GPA or RenderDoc. There's a whole bunch of cheats you can call manually to turn on debug annotations for all of your draw calls. The engine now just handles that on your behalf automatically, which is wonderful because it makes the setup a lot quicker. There is a tiny performance overhead when you're running in those modes, but it's not really noticeable. So this is our scene in RenderDoc. First thing I'll show you is that prepass mesh that I mentioned. So this is the one that we bake offline. We also do, we only use static lighting. So that's part of the reason that we can use a forward renderer. We don't have a ton of lights in our scene. Let's see here. Yeah, so this is that big mesh I mentioned. It's got a whole bunch of verts, but you can see it's basically the entire level in chunky granularity, but we get all the walls, and this allows us to exclude anything that we don't really need to run the pixel shader for. If I flip over here to our base pass, I think probably like right behind this wall is where my problematic wall was. So if we look at the history on that particular pixel, you're going to see that we do our draw here on this wall. Let's get that relay. Yeah, so you can see that draw call did happen, which is what we needed to get the color for that. And then there are things behind it, particularly this one. This shell is that wall that I mentioned before. You can see it failed the depth test, so we didn't actually incur the cost of the pixel shader. We just moved on with our life there. One of the other really nice things about RenderDoc, you can go in and run their pixel shader debugger. So if you're ever in a situation where you have a not a number or an infinity, you can actually step through line by line on your shaders and figure out exactly where that was introduced. This is incredibly valuable if you're ever writing your own shaders, or if you're defining your own render passes, or if you have a bug where you forget to bind some critical piece of information to the shader pipeline. This tool is just really wonderful. I love it, especially since it's one click to get a capture and get into it.
Seems like we might need you to do a tutorial on that as well.
So with all that as framing, now we can kind of look at the detailed results that we got from a split capture. So we have our full frame time, which is 17 to 18 milliseconds. Our prepass phase is that giant Z prepass mesh that I mentioned. So you can see it's a fat, meaty draw call. We're spending nearly 3 milliseconds in some of these scenes just pushing out to depth. But that cost keeps the mobile base pass third person low. Third person is where we're going to draw the environment. It's also where we're going to draw any characters that are in the scene. Mobile base pass first person is when we're drawing your gun and your arms in the first person view. We've then got some translucency work that happens, a little bit of post-processing, which is also based off the mobile post-processing path. For features that only existed in deferred or in the desktop renderer, we've manually ported the subset of features that we still want for our game. But it really is an art of getting just the minimal amount that we need to hit our art style and nothing else, because the perf budget is so tight. And then that final render pass is Slate UI. So I mentioned with the animation stuff on server that we've signed up for an ongoing support burden in terms of making sure we understand the anim graph. This is also true of all of the rendering work we've done because we've deviated pretty substantially from base Unreal. So whenever we take an engine upgrade, we spend a week or two just going through and making sure that our rendering code is playing nice with the base engine rendering code, forwarding any capabilities or bug fixes that Epic and the community have made that we want to get into our layer. Um, but it's one of those areas where we don't change anything in the engine without a lot of deliberate consideration because that maintenance cost is high. We could pin to a specific version of Unreal and say, okay, we're done. We're not going to upgrade anymore. But that would close the door to like tons of future improvements. So, like Epic is continuously adding things for performance. They're adding new capabilities that our artists and other folks in the editor want to take advantage of. Um, we're happy to pay the support costs to continue to take engine upgrades, but it does mean we don't do it unless there's a clear, tangible benefit. Wherever possible, we're going to try and follow best practices for Unreal Engine rather than roll our own.
Do you cherry pick that, or do you download the whole thing and then sort of merge them?
We take the entire thing. The general flow for that is we keep a version of the engine with none of our modifications, and then we've got our main branch, which is the version of the game that we're currently running. Whenever we're doing a big engine upgrade, we take all of Epic sources, we integrate that into what we call our integration branch. We also take the latest version of our game from the main branch, and then we spend about 4 weeks going through, merging all the conflicts, making it compile, running a bunch of testing, fixing all the rendering issues. It's a pretty meaty process, but it's not even close in terms of cost value trade-off. Like the benefits of each engine upgrade far outweigh that month of engineering effort to continue to take the upgrades. So these are specific timings. Let me show you what the raw data looks like. This is a screenshot of GPA. And the reason it's a screenshot is because if I open this capture on my development hardware, you're going to see timings from my machine rather than from the laptop that this was captured on. At the top here, you can see the full frame time. So this was 17.6 milliseconds. We were running at 57 frames per second. There are 383 draw calls in this particular scene, and what the user has selected right now is 1200 microseconds. Is that text clear over the screen?
Yeah.
I hope you can.
Yeah, we can see that.
Okay. Okay, cool. Over on the left here is all the individual draw calls. You can see we've got 4 draw calls selected. This is the mobile-based pass first person, so it's just the weapon and the arms. So that's kind of low spec. I can show you on my machine that exact same scene. Let's crack this open. What you're going to see here is the timing looks quite a bit different. Recall that this was 17.6 milliseconds. On my development hardware, it's 427 microseconds. So if we were perfectly efficient and had no CPU work, we could be rendering the scene at 2,342 frames per second, which would be pretty darn good, but it puts into perspective just kind of how optimized our rendering layer is. Obviously, we don't hit 2,300 FPS on high-spec machines. I wish we could. This is running, my dev box has got a 1080 Ti in it. So this is a relatively recent GPU, but it's not like an RTX 2080 Ti or something. This is not a wild result for folks with modern hardware. So on high spec, we tend to move from being GPU bound to being CPU bound. And this surprises a lot of players. Players are used to modern games being GPU bound. And often we hear players saying, hey, I went into my graphics quality settings, I turned everything down and the game didn't get any faster. And that is because we're CPU bound. So in our game and in most Unreal games, there are 2 threads that are really important. There's the game thread, which is responsible for handling input, updating game simulation, laying out and setting up the UI. Then there's the render thread, which is responsible for setting up the scene, doing visibility checks. That's where like frustum culling and occlusion culling happen. Then we go through the scene and build all of the individual draw calls that need to get sent to the graphics API. In the engine's code base, graphics APIs are abstracted behind a render hardware interface or RHI. And the way the render passes work is basically they build a bunch of commands against this abstract RHI concept, which then goes and gets executed against the actual graphics API. But we build up a command buffer. Then when we're ready to actually send it on, we flush that command buffer to the graphics API. In our case right now, we just support D3D11. It's possible we'll support D3D12 or Vulkan at a later date. We're still evaluating those. But right now we're on D3D11. So something that we turned on recently, which I think Epic added in 4.17 or 4.18, is called the RHI thread. And what the RHI thread does is, rather than having the render thread actually flush the RHI command buffer and execute all those calls against the graphics API, we can have the render thread continue to work on just setting up the scene and figuring out what commands need to go into that command buffer rather than waiting for it to do the execution. So we have that behind a setting right now in our game called multi-threaded rendering. When you turn that on, there are some scenes where you'll get a pretty substantial performance improvement. Out of the box, stock Unreal, I don't think has the RHI thread turned on D3D11. We had to do a little bit of work to make that work, as well as some changes to our renderer to play nicely with it. But once we got that all up and running, it's worked great for us, and it was a relatively light touch modification. Let me show a video of the results. I've showed this live, but it's hard to do a side-by-side comparison. So before I get into this, I want to caveat that this helps in scenarios where you're render thread bound. It doesn't help in scenarios where you're game thread bound. So if you're in intense combat, we tend to be game thread bound. The game simulation is the most expensive thing in that scenario. If you're just running around the map, or if you're alone in the practice range, often modern hardware tends to be render thread bound. So the GPU is not doing very much work. The game simulation isn't doing much work, but it is a lot of work to just go through the scene and set it up for the GPU to go and execute against. So in those scenarios, that's where this provides the biggest benefit. So what you're going to see in this video, on the right, I've got multi-threaded rendering on the left, I've got it off. And if you watch the charts, these are game reported timings for FPS, game thread time, render thread time, and RHI thread time. And when multi-threaded rendering is on, you're going to see work move from the render thread to the RHI thread. Whereas when it's off, all that work is just happening on the render thread, and it becomes the bottleneck for the game. Below that, I've got stats from RivaTuner. I just like to have RivaTuner running as a sanity check for what the game itself is reporting. Since RivaTuner works across any D3D11 title, I can more easily compare to the experience in other games. So as we run through right here, you can see in this scene, we're about a millisecond faster with multi-threaded rendering on, which is nearly 100 FPS at these numbers. It's a huge difference. I think it's going to move here in a second. So another scene right here, you'll see that render thread is taking about 3 milliseconds, whereas over on the right, the render thread's taking 1.3 milliseconds, and the RHI thread's taking about 2 milliseconds, which moves the bottleneck off the render thread. And then same thing here, right? Like if I pause, 511 frames per second with it on, 349 frames per second with it off. You'll also note that my GPU load is higher. That's because we're making the GPU draw more frames when multi-threaded rendering is on. We're doing a better job of getting work to the GPU. Yeah, so that improvement is in, and it's live, and it helps a lot in scenarios where we would be render thread bound, but it doesn't help much in combat. So let me kind of show what combat looks like and some of the things that we're currently thinking about. So this is a profile that was generated from our game. And this is in a heavy combat situation. So this is like a 5v5 team fight where guns are firing and abilities are being triggered. Each track here in this image is a thread. The very top one is our game thread. The second one is our render thread. This third one is the RHI thread. And all of these folks down here are task graph threads. Let me put some annotations up. Excuse my poor handwriting.
I think it looks good.
So you can see here we've got 3 full frames in this image. We've got 1 frame that's partially cut off here. You can just sort of think of the x-axis here as timing. And what you'll see is kind of all the big chunks of the work that's happening in the game. So in the game thread, we're handling input. That doesn't take very much time. There's the game simulation, which is by far the meatiest part of this profile. And again, that's just because we're in the middle of that 5v5 team fight, and there's a lot of stuff that has to happen to accurately run the simulation. When the game simulation completes, the game thread has to do a little bit of work to send updates about dynamic actors to the render thread. So like new position of characters and weapons and abilities, that all gets sent to the render thread after the game sim. And then we've got a chunk of time that is spent on layout and updating the UI. This is another area where we've done some optimization. We're probably going to invest more here in the future. We feel like it's a little bit more expensive than we'd like, and so we can still probably do some reductions here. On the render thread, we take all that dynamic state that came in from the game thread. We do visibility and culling. So that's where we're going to do the frustum culling, do the occlusion culling. And we go through and do the scene render passes. This is where we're actually building up those RHI command lists that I mentioned before. And then finally, we do the same thing for UI rendering here at the end, which is very cheap. You'll note these big purple and blue chunks. This is where the thread is just sitting idle. And that's because it's waiting on new data from the game thread. When we're not in combat, there's a lot less idle time here. And in fact, there might be idle time on the game thread instead. That's when we get into those render thread bound scenarios. But in combat scenarios, we're fully game thread bound on high spec machines. On the RHI thread, you can see that as soon as the scene render passes start creating work, we hand that off the RHI thread, and it can start executing those commands against the graphics API that we're using. And then finally here, you can see the D3D11 call, which is going to put the image on the screen. So something that is interesting in Unreal, generally the renderer is allowed to run one frame behind the game simulation. The reason that that's true is if you didn't do that, your frame time would basically be all of the game work, then all of the render work, and then all of the RHI work, and you'd have fat frames. So instead, what we do is we let the game simulation continue. So it starts working on the next frame while we finish rendering the previous frame. So that's why there's a little bit of overlap here. On the task graph, we can run any asynchronous tasks in parallel. In general, what we'd like to do is move more work from the game thread to the task graph. You can see these blue chunks are where these threads are just sitting idle. So there's a lot of opportunity to use cycles on these other threads for machines that have enough cores to do more parallelization. Today, we do some animation work on the task graph. We do particle work on the task graph. We do in-frame updates. We set up occlusion queries. So this is where Umbra is figuring out the world state that is going to be needed for the Umbra culling queries. We also do render path setup on the task graph. So an example of something that we can parallelize, like parallelization in general is hard. We can't just like flip a switch and take parts of the game simulation and move it to the task graph because you introduce all sorts of concurrency issues and complexity around managing state across threads that could be mutating or reneeded at different times. But there are some scenarios where it's fairly straightforward. So an optimization we recently made, show you a feature here. We've got a feature that we call minimap vision cones. And what minimap vision cones do, I'll show once my Pi session launches, is over on the minimap, we draw a cone that shows what you're looking at as well as what all your teammates are looking at. And so this is super useful if you're like on a bomb site and you want to make sure that every point of ingress into that bomb site is covered by somebody so that you're not surprised and potentially getting shot in the back. Let me maximize here.
Yeah,
you
we
can see
a little low bit rate from your end. I think it's about to catch up here though.
Okay, can you see the white outline on my minimap here? As I kind of pan back and forth that cone.
Somewhat the lighter gray.
Yeah. So that's really it. You can see right now as I'm looking down this angle on my mini-map, there's a cone that kind of shows what I'm looking at. If I turn and look at this other angle, you can see that I'm looking at that angle. We get this for all your teammates as well. So you can see what's covered and what isn't covered. Right now, a teammate could look at their mini-map and say, hey, Marcus could be surprised by somebody coming from his right. But that's really what the feature does. It turns out we don't need 100% up-to-date information in order to produce a useful minimap vision cone. It's okay if there's a frame or two of latency there, especially if you're talking about running at 200 frames per second or something. If my exact angle of that cone is off by 5 milliseconds, it's okay. It's going to be imperceptible. So the way that works now is we move that computation to the task graph, and the game thread just periodically sends off new updates and then reads whatever the latest update is. And even if it's a frame or two old, we can still show useful vision codes. So that's the type of thing that's easy to move. Things that are harder to move are the actual simulation for what characters are doing, simulating moving, shooting. But that's an area of investment that we're looking at. At this point, for the types of frame times we're talking about, there really aren't like wins on the order of half a millisecond to a millisecond anymore. We're really fighting tooth and nail for tenths of a millisecond. So anytime we can see a 0.1 millisecond improvement, like that's an area that we're willing to throw engineers at and try and make it better. But yeah, like that's sort of where we are today. We want to make high spec perf even better than it is.
Super exciting. I don't think I've seen such a quick, nice, thorough breakdown in what that was about 45 minutes, I think.
Yeah.
It's clear that there's a lot that went into each and every step of the way to get here. And so if you're ready for it, I definitely have a good chunk of good questions from the people watching.
Yeah, let's do it.
Cool. And I should mention that the bitrate still seems a little bit low, but hopefully it will catch up in case you need to show something else.
Okay.
One of the first questions that came in was, how long has Valorant been in development?
So I believe the project originally started like nearly 7 years ago at this point. Now that's very small, like a few people in a room prototyping. I joined the team about 3.5 years ago, and I think we were in I think we were starting pre-production at that stage. So I've been here 3.5 years, and the team has grown a ton since I joined. I think it was like 40 or 50 people when I joined, and now we're over 150, maybe nearly 200 at this point. It's been a while.
Someone else was curious if you could give a rough blueprint to C++ ratio. How much is blueprint? How much is C++? And did it change over time?
So like our core systems tend to be in C++. Like we have a bunch of base logic for like what even is a character in our game, what even is a weapon. We have core classes, but then the vast majority of our actual game logic is built in Blueprint. All of our character designers build all of the abilities in Blueprint. Occasionally, we'll need to add some C++ tech to support that, but we use Blueprint heavily. We don't want to require programmers for game logic if we can help it. But core moving and shooting, doing prediction, doing rewinding, things like that do live in C++.
Are you utilizing the built-in nativization feature for blueprints?
We're not right now. We evaluated it when it first came out, and it didn't yield compelling results for our game. And I think if you look at the documentation and if you go back and look at some of the talks at the time, nativization provides the biggest benefit on a blueprint that's like just doing a ton of math.
Mm-hmm.
If it's calling a C++ function that's expensive already, like nativizing the blueprint calling that C++ function doesn't really help. I suspect there are areas where we could get some wins out of blueprint nativization, but we need to go back and do another evaluation pass on it.
It also adds a layer of complexity of making that change, right? So if you're not seeing too much of an improvement, then it's nice to cut away as much complexity as possible, since you're all humans.
Right. Totally.
Let's see. There were some questions regarding the, I think, anticipation and prediction. Let me know if that's something you don't want to go into, but how does movement anticipation work? Is it based on how the consumer, I think it means the player, has played during its history with the game, or based on test players' experience?
I'm not the best person to speak in depth with regards to how movement works. In general, though, like I think like a super simple view of it is like the server knows what your inputs are at any given time, and we can continue to predict based on those past inputs. There is a point where, like as I mentioned, we're server authoritative. So if you try and do bad behavior on a client, like a lag switch, there are thresholds baked in there where the server will override what the local player is trying to do. So you can get a server movement correction even for your local inputs if you're playing in poor network conditions, or if you pop a lag switch and try and come around a corner. Like we don't trust the client. In good networking conditions, it basically should feel just like it would feel if you were controlling everything locally.
Did you customize the stock character movement prediction?
Yes, heavily.
Let's see. To the environment. How is the environment loaded? Are there any persistent and sublevels?
We use sublevels. We don't use that for loading. We use it for being able to work on the level concurrently among a bunch of different artists. So I can kind of show in the editor, maybe, where's my level view? I've got a bunch of stuff turned off here just for demo purposes. But you see, yeah, we've got a ton of different sublevels, and they're generally done by geography and also by capability. So like we have a gameplay layer that has a bunch of invisible volumes that we use for various things, like the map callout, seeing where you are. We've also still got like gray box stuff, which we use for prototyping. And then in the actual arted up environment, we separate it by region of the map. When we load the level, we load the entire level. We don't stream anything in and out today. So like when you go through the transition from character select to the game, we fully loaded the level by the end of that. If we had a bigger world or we're an open world or something, then streaming volumes and all of that would come into play. But in practice, we can fit everything in memory.
Did you do anything specific to minimize input lag, or just try to get it the whole frame as fast as possible?
We have done a bunch of testing around input latency, and we have done some customizations there, but I am not the best person to speak to the details. I can tell you it's very important to us, and we've measured it carefully, and we've run a bunch of labs around it to try and keep it as low as possible. One thing I can speak to that is specific is, I mentioned the renderer can run a frame behind the game thread. We did a bunch of experiments early in the life cycle where we actually disabled that so that what you were rendering was always the exact same frame that we just processed the game simulation on. What we found is that made the frame sufficiently larger that it actually made input lag worse. The frame rate increase that we got by allowing to run one frame behind gave us a perf win. We don't let the renderer get more than one frame behind, though. So you can't get like a huge spread in latency. You're always going to be within 1 to 2 frames.
I believe you mentioned earlier that the question goes, replication was highest cost, correct? How did you drop replication costs?
So I think at the time that image was taken, we had basically done no optimization around replication. I didn't work on replication, so I don't want to get too much into it, but it was a combination of making sure that we replicated only the things that needed to be replicated, and also building a bunch of patterns around how to do best practices in our game. So there were a bunch of things that were like continuously replicating that it turned out we could replicate only on demand when they changed. We have a whole bunch of logic about like when something is idle versus when it needs to be replicated. So like a good example of that is like, we don't need to replicate the state on your pistol if your pistol is holstered and the thing's changing, right? We can make it dormant. I think we also did some customizations to the replication code in the engine, but I don't have the details of those offhand.
Let's see.
I can also say just one more thing on that. The other thing we did is we built some automated tooling. I think it's in a commandlet, and our continuous integration system will periodically run that commandlet and detect anything that's replicating. And we've basically got an allow list of everything that is known and is allowed to replicate. So if we have a regression where something new starts replicating, we all get an email about it and somebody has to go and investigate.
That's not the email you want Friday night. How did the team land on using Umbra? How does it differ from the built-in static visibility calculations?
So we used pre-computed visibility way back in the day. I don't have the numbers handy, but basically we tried it. We tried Umbra. We found Umbra produced better results, and we switched to that. But the big caveat on that is we did that evaluation like 4 years ago at this point, and so any commentary I'd make on PBS today would be outdated.
Fair enough. Fair enough. I'm curious, what version of Unreal are you currently on?
We're currently in 4.23. We'll probably update to 4.24 sometime in the next few months. We're starting to do prep work for that. Generally, we like to stay about one version behind latest. And that's just because our engine integrations are expensive, right? Like it can take about a month. So like when we move from 423 to 424, we want to be reasonably confident that like all the hotfix releases are already in 424 before we pay the cost of doing the upgrade. And that helps both for our internal stability in case there are any crash fixes that are going to come in, and also just in terms of like managing the integration. But yeah, generally we stay about one version behind, which means we're generally doing about 3 engine upgrades a year.
In case you know, what are the performance measuring techniques used for animation overhead on the game server?
So I'm not really sure I totally understand the question. I can tell you how we measure it. Is we added instrumentation to all of the animation code, basically. So like that subsystem metric that I showed is like a roll-up metric of everything that we've tagged, and it's like, hey, this function is involved in animation. We do have a lot more granular measurements, and also, of course, you can also measure with the stat system that's shipped in the stock engine. But yeah, I mean, largely it's we instrument, we measure, and then like we look at that code and make it faster.
Nice. Someone was curious how you created the graphs for the render threads.
So that is actually a view from, you're talking about the image I showed here. This is an image from Chrome's tracing view, actually. We have an internal profiler that we use on internal environments where we've added a bunch of manual instrumentation. And when we dump a profile, it drops a giant JSON file into our logs directory, and it's in the format that Chrome's tracing view knows how to understand. We sort of overwhelm it a little bit because these files tend to be like 200 or 300 megabytes, which is not really what Chrome's tracing view is designed for. But it works really well, and it meant we didn't have to build a custom viewer.
Nice. Let's see. Someone was curious if any of the VFX in Valorant is made with Niagara.
We're on Cascade right now. We're looking to move to Niagara now. On 423, Niagara is still considered experimental, I believe.
Correct.
I forget if it became released on, is it 424 or 425?
25 is...
25. So I know we're starting to pilot some stuff on Niagara, and I know that our VFX artists are excited about using it, but it's too early to know how much we'll move over until we can start building it and also really get perf results.
Yeah, once again, when you have a pipeline and a workflow that works, it takes a lot of effort just to switch, right? And so you need sufficient enough reasons to do that, to invest that time and work into it.
So that's definitely true, but I mean, we are a live game, right? Which means if there are workflow improvements, we're willing to invest the time to go and make those workflow improvements. But we're, since we're a couple versions behind right now, soon to be just one version behind, we're still not on latest and greatest. And so probably we're about 6 months away from really looking at Niagara in earnest. It'll be whenever 426 is out and we're upgrading to 425.
Might ping you on the forum thread in 6 months to a year and see how that went.
Totally.
Let's see. With Valorant's ability system, are you using the built-in gameplay ability system?
I don't actually know. I think we might use some parts of it, but I think most of what we've done is custom.
Let's see, going into organize a little bit here. The game is 8 gigabytes. What is the max resolution of, he said materials, I think he meant the textures.
We have, most of our textures are fairly small. Like you're not going to see a bunch of 4K textures in our game. We do have a few textures that are relatively large. We have a couple of cube maps that we use. But by and large, our textures are pretty small. You're going to see a lot at 512, maybe some at 1K. But yeah, we're very cognizant about texture sizes. We care about it less from the install size and more about VRAM size.
Do you use...
install size is important, but not for textures. Sorry.
That's all good. Do you use neural network AI at all?
I don't think so, no.
Let's see. These are all new questions that come in, so I haven't had a chance to go through them yet. Someone was curious what the tool were called, where you were showing off where you could see each frame breakdown. Is this available in the engine, or is it a custom solution that your team came up with?
Are you talking about RenderDoc and GPA?
I believe it was
If so,
RenderDoc.
like, yeah, RenderDoc and GPA are publicly available tools. They're not proprietary. They don't ship with the engine, but you can go and download them on your computer for free. Uh, the thing I did mention is there is a plugin for RenderDoc that ships in the engine, which if you just check this box and turn it on for your project, that does make it a lot easier to take a capture. Otherwise, you've got to figure out, hey, how do I attach RenderDoc or GPA to my editor or my game, and what are the hotkeys I need to press? What are the cheats I need to turn on to get useful information? But both RenderDoc and GPA have a ton of documentation, and also there's a bunch of public talks on them already. They're not specific to Unreal.
Yeah, there's quite a bit of information on them. We mentioned them before. I'll make sure for all you are curious about them to add links under the resources section of the forum announcement post of the stream. Easy way for you to make sure you get the right spelling and find the right tool. Someone was curious if you'll be releasing mapping tools.
I don't think that's something we have plans for right now. Our priority is really on making sure we have a good tight game with a good gameplay experience. Something like that might be something we'd consider eventually, but that's not something we're looking at right now.
How do you handle the game simulation if the client falls behind in performance? Do you resimulate all the missing ticks in one frame? Do you reschedule them, or do you skip ticks?
Well, I mean, we don't have like a fixed tick rate for the client. So you're gonna, if you're running at 30 frames per second, you're gonna get 30 simulations per second. The exception to that is the server simulates movement at a fixed rate. And so if your client falls behind in terms of movement updates, the server is going to create movement updates on your behalf. And that's to make sure that, if you're doing something nefarious, or if you're playing on a weaker computer and can't keep up, we still want to have a smooth experience for everyone else in your game. We don't want you jumping around at 30 frames per second.
Do you have a target byte size per frame per client?
Target byte size. I'm not sure what you mean by that.
Me neither, unfortunately. See if that person could provide a little bit more details, and we'll get back to the question. You mentioned having designers making abilities and such in blueprints. Has that lessened the need for programmers on the project aside from C++ nativization?
So yes, right? Like if we were trying to build all of our gameplay just in C++, that would take a lot more programmers. I think some of our designers could write code, but many of them are not coming from a programming background. Also, like the iteration time in Blueprint is just so much better than C++, right? Like you don't have to recompile your code. You can just update that blueprint, run a Pi session, and see if it works. So yes, it's reduced the need for programmers. I think in the absence of a system like Blueprint, if you look at a lot of games, they come up with other solutions for scripting so that you're not constantly having to go and update a bunch of game code.
Let's see. Do you run automated tests, and what sort of automated tests?
We do. We run automated tests. We're not on the latest version of the automation framework that ships with the engine. That's something we'd like to evaluate. This is kind of another example where at the time where we stood up our automation solution, there wasn't an engine solution that met our needs. So we have a handful of automated tests. It's less than 100, but they do smoke testing of big pieces of the game and make sure that it continues to work. That's actually incredibly valuable, especially when we're doing like an engine upgrade, because we found issues where something fundamental is broken, and it can help us detect and correct it. We run that automation after every build that we produce, and we produce a build every 10 minutes if there's new changes. Not end-to-end build time, but in terms of like we kick off a new build every 10 minutes internally. So if something breaks one of those tests, we all get a notification, and we can either back out that change and go and fix whatever issues introduced. We also do what we call monkey testing, where basically we spin up a server, we spin up 10 players, and we have those players just spam random inputs for hours at a time. And that's good for just detecting like, hey, there's this weird sequence of events that can potentially lead to a crash. So we do get crash telemetry and things like that. And if our monkey testing is able to take down a game, that's obviously something that we treat very seriously.
Are you using any LODs on the environment?
We are. I don't have the details of those handy.
I'm just gonna keep rapid firing here until until we're done.
Sure.
How are the HUD elements implemented?
I mean, they're UMG widgets. We have some C++ code that supports that, but a lot of it's just built in UMG in the editor. A lot of the things that are like sort of interesting are making sure that we have clean data models to feed those UI elements. There was a time in the project where our UI was like, pulling state directly off like a player gun, and that's really not the right way to structure that content. So there has been some investment there, and I suspect there will be ongoing investment there over time. But yeah, it's all pretty stock stuff. We haven't done many customizations there.
Have you used or looked into Unreal Insights?
Not yet. It's something that's on our radar, but we haven't used it yet.
It's still in beta, so
Yep.
that's a good question. Do you use the projectile movement component, or did you have to handle your own projectile code to do server windup during replication?
I don't know how much or if any of it from the stock engine that we've used. Most of our bullets are all just hit scan. So it's more, I'm simplifying here, but basically you can think of your gun has a certain accuracy based on like your movement and your fire rate. We have some unit that goes on there to figure out whether you're going to shoot exactly down your aim vector or if you're moving. We fire a ray trace. It's actually several ray traces because that's relevant for doing wall penetration computations. But it's mostly hit scan. We do have a couple of exceptions to that. Namely, we have the Bucky shotgun, and the Bucky shotgun has a right-click fire that fires a puck that then explodes. That puck is a projectile. Also, if you look at our character Raze, her ultimate is a rocket. That's also a projectile. It's not a hit scan rocket. But yeah, all of our movement and our shooting code is like highly customized just for our game, and a lot of hours have gone into making sure that it feels just right.
How are you managing actor/blueprint state in a way that supports server rollback?
It's complicated. I can't give you a general purpose answer, but like the short of it is everything that needs to be involved in rewinding has to be aware of rewinding. So like our skeletal pose components, or sorry, our skeletal mesh components, like have code in them that know, hey, we might need to go back in time. So what does it look like to roll back to a snapshot and then restore back to present state? I mean, all of that code only exists on the server because the client doesn't do rewinding.
Let's see. Did you use UMD widgets to create your real-time RHI multi-thread graph overlay? I believe that was a different tool, right?
I think you're talking about the performance graphs. Yeah, I believe that's just a widget.
They might.
In fact, if you use like the stat unit sheet in the engine, like there's already code in Unreal that like knows how to draw a graph. I'm not 100% certain, but I think we basically just reuse the same code that the engine uses for some of its internal debugging graphs.
And then can you double down on what the tool was used when you were comparing the two individual scenes, when you were multi-threading and when you were not on the render thread?
Oh, for that, I just took two videos and then edited them together in Premiere.
Oh, I meant
or you mean the timing? That was
correct.
Riva or statistics server.
Riva Tuner. All right, I'll make sure to drop a link to that in the resources section on the forum announcement post as well.
That's it's a pretty cool tool. You'll see like a lot of like video game review sites and stuff will use that tool to measure frame rates, and it's very customizable. So you can figure out like what stats you want. If you want, you can get like the core temperature of every individual CPU processor you have. But it's super flexible, and it's a great tool just as a gamer, not even as a game dev.
I guess I was curious, when you were doing that snapshot of the two different scenarios, did you just run similar through the map, or did you have something automated that would move the character?
That was all manual. I literally just fired up the game, ran, and so you might note in the video all of the movement only had one view, and that's because the way I captured it is I did all the movement and then I went into my settings menu and changed the setting. So the scene for the comparison was all static. I wasn't moving. The camera wasn't changing. But yeah, I mean, it's a lo-fi test. I'm not doing anything fancy there.
That's why I was wondering. Uh, it's a good question came in. What are you using for audio and voice over IP?
We use WIs for audio. For voice over IP, that is a custom solution that I don't know the details of. Our voice over IP actually runs through the launcher, not through the game itself.
Let's see. I think those were all the specific questions, sort of to more related to your topic, but there are a few more general, and I believe we have a little bit of time. They
Sure.
were curious if you're planning on doing any more presentations about the development of Valorant in the future.
I don't know. I do know in general, our team is trying to do a lot of comms wherever possible. So like we have a tech blog where we talk a lot about implementation details of specific topics. Also, like there was a great article that went up yesterday from the map designers on like what we were thinking about when we built Split. But if you just look at like the Riot Games and the Valorant blogs, that's where a lot of our stuff is. And I'm sure in the future, like we'd be happy to talk more about stuff if folks find it interesting.
Yeah, I'd be curious to maybe have you back on the stream in a year or two and sort of see how it went and how you're looking at the development today. And then, after a year or two of players, which always adds, it's that thing you don't really get as much of during development, but once the game's live and you have everyone playing it, you learn so much about it, right?
Yep.
It'd be interesting to see how that went for you all.
Yeah, and like to that point, right? Like we sort of think about launch as just really the beginning.
Yeah.
If you look at kind of the way League of Legends has run over the last decade, right? Like it's a very different game than it was 10 years ago, and I suspect that will be true of Valorant. We're in this for the long haul. We're gonna keep iterating with the community and with players, and hopefully build something really special. Just hope folks are having fun with it.
All right, we're getting a few more technical questions coming in. Could you give an example of a module class/system, if any, that you had to move from blueprints to C++ for optimization?
Um, I don't know that I have a good one handy. I can talk about sort of like what we've done in C++ rather than Blueprint. Sort of like I don't know that I would think about C++ versus Blueprint in terms of performance. That might be different if we were only a Blueprint shop, because of course there are going to be things if you're fully Blueprint that are just going to be slow with the overheads. Like the example I like, again, going back to I think the original talk when Epic built Blueprint nativization, was if you're just doing a math function over and over in a tight loop, it turns out the overhead of executing the blueprint and doing the swaps were more expensive than running that simple math. But for us, basically, like any big meaty system that isn't going to change much, we're comfortable putting in C++, right? So like, again, that core shooting, that core movement logic, that is going to live in C++. But if we're, wanting to build a new ability, and especially if we want to iterate on it, and even if you look at the live game and the patches that we've released since closed beta, you can see there are pretty substantial changes to the way some of our abilities work. So having the ability to iterate and tune, having that logic all live in Blueprint is super valuable to us. Because otherwise you're going to slow down that iteration loop if you're having to go and edit code to make that happen.
How long did it take for the environment team to make a level?
That is difficult to answer because the game has gone through a bunch of different incarnations. If you look at the Ascent map that we've now shipped, there have been versions of that map for years. It's changed a lot since the original version. When we are early on a map, we build out a gray box level, which just has basically super grid walls and floors and some details, but doesn't have any art. And we do a lot of playtesting on gray box before a map moves into like an art or a production phase. And so if you look at the article that the map designers published on Split yesterday, it talks about some of those earlier incarnations. And you can kind of see the layout of the map and how it's evolved over time. Obviously, like once you've arted up a level, if you're going to make a dramatic change to the layout, that's a lot more expensive. So we want to be really confident that a level is playing well and that it's fun before we go and build it out for real. And the maps team in general, like once they're at the point where they want to build something out, they have a really good production pipeline for what that looks like. But the total life cycle of the map, I mean, it can be years.
How do you manage memory handling? For example, Blueprint doesn't handle struct pointers, meaning that structs gets copied all over the place. Do you have anything to measure or mitigate that?
So not that specifically. We are keeping an eye on memory. We have occasionally run into issues where we exceed our memory target. We try and keep it under 4 GB. We've actually had quite a bit of trouble getting accurate profiling, and I don't know if that's because of changes we've made or if it's because of the way the engine handles it. There is the mem report sheet, which gives like a good overview of a bunch of stuff that's loaded. We've also looked at the low-level memory tracker, and that helps quite a bit. But at least in our code base, there's a fair amount of memory that is uninstrumented, and so that's something we're actually driving on because we want to make sure that we remain within our targets. We are fortunate in that, like, we sort of have a handle of what's going on in our game. It has a pretty well-defined structure. We actually don't run garbage collection during gameplay. We only run garbage collection when the round ends, and that's just to keep the gameplay as tight as possible, right? Like even if it's a tiny 10 millisecond hitch to do garbage collection, we don't want that while you're trying to fire a gun. But as a result, it means like we're not doing a bunch of dynamic memory allocations while the game is running, which then means basically we see what it's like when we reload it, and either we're in budget or not. And if we're not in budget, then we have to go and fix it.
Have you considered Vulkan, or what was the reasoning to prefer Direct 3D?
So we have considered Vulkan. We haven't fully evaluated it. We might support it at some point in the future. We haven't closed the door to that, but we also just haven't done the work. Earlier in development, we chose D3D11 because that was what all of the hardware we were targeting supported. But in the future, I think it's very likely we'll support either D3D12 or Vulkan.
See, someone's curious on the garbage collection question. No garbage collection? Does this mean custom object pooling code?
We do have custom audio pooling code, yes.
And then I think to clarify, you do the garbage collection between the rounds.
Yeah, so we basically run garbage collection. Like, our rounds are generally about 2 minutes long. So while gameplay is happening, we pause garbage collection. When the round ends, there's a little transition where we reset everything. You go back to your spawn. You get an opportunity to buy new weapons and abilities. At that point, when we're doing that reset of the world state, that's when we run the garbage collection.
I think that was it. Questions from chat. I was a little bit curious, who's your favorite character and why?
So I think if I'm honest with myself, Phoenix is my main. I like Phoenix because I can't consistently hit headshots, and so I have a lot of engagements where if I win the engagement, I've probably taken some damage because I got that kill by getting body shots. And so Phoenix is nice because with his ability to self-heal, he can erase mistakes and set me up for the next engagement. Aspirationally, I want to be good enough to play Jett. Jett's kit, especially with her ultimate, really only shines if you're consistently hitting those headshots. So like, that's the skill set I need to practice to be able to main Jett.
How much Valorant per week do you play? And I will state that it's sort of outside of your work.
So it varies a lot. Right now, I'm generally at the end of my day, after I wrap up my professional and family responsibilities, I hop on Valorant for like 3-ish to 4-ish hours a night. Not every night, but most nights. So probably like 20 hours or so a week.
Will you go in and just play with a bunch of randoms, or do you usually join with a team of friends?
Both. I do solo queue if all my friends are busy. I prefer to like get in a group with folks that I've played with before, but especially right now, like, I'm just having fun playing the game. Something that is like maybe non-obvious about development is, even though like I've been working on and playing the game for years, until we actually hit closed beta, like, there wasn't a population large enough that like we could just fire up a game,
right?
At night and play. It's always a lot of work to organize 10 people, and even when you're doing that organization, you're going to have high skill disparity where you have some people that are just like incredibly good and others that are incredibly weak. It's difficult to get like a really tightly tuned experience and just bang out games until it's actually in the hands of players. So right now, since the start of closed beta through now, I've just been like enjoying having the ability to like finally play this thing that we've worked on for so long.
And that must feel really good, right? Because it's different. It's a difference from like a highly competitive multiplayer game versus developing a single player game. Because the single player game, it's just you and the game, right? And so you pretty much get that, or I would think, throughout the testing that leads up to release. Whereas in your case, everything changes the moment it's live, and people get to play it for the first time. They get to get better, and so
Right.
it's cool to hear.
It's also different. Like we play test a ton internally because like, that's how we get the tuning right. That's how we make sure the maps feel good. That's how we make sure the abilities all make sense, right? Like it's driven by internal play tests. But sitting down to do an internal play test to test some specific changes for like an hour is very different from saying, hey, I'm going to sit down for 3 hours and just bang out some games. Because like, I don't know about you, but when I play, like I'm usually pretty trash my first game. It takes me a game or two to really get warmed up and have it start clicking. And while we have had opportunities to do that internally before we shipped, it was much more expensive in terms of a transaction cost, feeding a block of time where you could get enough people to play for a big block of time. Now it's just like I just queue, right?
Yeah, that's really cool. And they don't even know, right, that you're kind of analyzing the game a little bit, and sort of the changes that you've made that are now out
Yeah,
live.
for
That's
sure.
cool. Marcus, thank you so much for coming on the stream, giving us very deep dive into some of the performance requirements that involves for the game. I hope to see you back on the stream one day. Like I mentioned, it would be really interesting to see, in a year or two, what has happened and what has changed, and sort of how the development of the game progressed. And so, yeah,
That'd
big
be
thanks.
fun. Let's do it.
Yeah, hope you had a good
Thanks so
time.
much for having me. This
Yeah,
is wonderful.
absolutely. And for everyone else out there, next week I'll have Grayson Edge on the live stream, and we're actually going to talk about Sequencer in 4.25. He has prepared a presentation for us, so make sure you tune into that. If you are looking for opportunities to connect with the greater Unreal Engine community, you should head over to communities.unrealengine.com, and you can sign up and try to find a meetup group in your area. And as I'm sure you all know, and as you can tell from the stream as well, there are no physical meetups at this time. However, the meetup group leads have spent a significant amount of effort into trying to still organize virtual meetups, and I even believe that there's a little bit of cross-sectional meetups happening between them to sort of connect with other people around the world now that most of us are spending our time on the internet, a little bit more at least than we normally do. And I think with that said, it is time to, at the 1 hour and almost 30-minute mark, time to say goodbye. But we hope that you are staying safe and that everything is well with you and your families. And until next time, we're going to say goodbye. So bye, everyone. And thanks again, Marcus.